space enthusiasts, and welcome back to the RedMars Podcast. Today we're strapping in for a thrilling ride through one of the most awe-inspiring and complex feats of human engineering, space launch systems. Have you ever watched a rocket launch and wondered what goes into sending payloads, satellites, or even astronauts into orbit? From the thunderous roar of the engines to the precision required to hit the right trajectory, launching a rocket is a symphony of science, engineering, and raw power. Today we'll uncover the history of these incredible machines, the designs behind them, their costs, the engines that power them, and how they aim for different orbits. Whether you're seasoned space enthusiasts or just curious about how we get to space, this episode has something for you. So buckle up, it's going to be an exciting journey. So let's start with, what exactly is a space launch system? Well, at its core, a space launch system is any vehicle capable of escaping Earth's gravity to place payloads, whether satellites, probes, or even humans, into orbit and beyond. These systems typically consist of a rocket. This provides the thrust needed to overcome Earth's gravity, some sort of payload, which is the cargo being delivered into space. This can be scientific instruments or even astronauts, and a launch pad and support infrastructure. This is the ground-based systems that prepare and ignite the rocket. Space launch systems are marvels of engineering, balancing extreme power with incredible precision. To reach space, rockets must reach a speed of approximately 28,000 kilometers an hour or 17,500 miles per hour, a velocity known as orbital speed. Achieving this involves overcoming immense challenges like atmospheric drag, gravity, and heat. So let's start with a history of space launch systems. Well, the history of space launch systems is a story of human ingenuity, perseverance, and unrelenting desire to explore the unknown. Let's dive deeper into the milestones, pioneers, and breakthroughs that shaped the incredible journey from early rocketry to the modern era. So the dawn of rocketry. The story begins with early experiments in the 20th century, led by visionaries who laid the groundwork for modern rockets today. Robert Goddard, often called the father of modern rocketry, Goddard launched the first liquid-fueled rocket on March 16, 1926, in Auburn, Massachusetts. His rocket flew just 41 feet, but it proved a crucial point. Liquid fuel could provide the sustained thrust needed for space exploration. Goddard also pioneered gyroscopic stabilization, steering via vanes, and multi-stage rockets, ideas that remain integral to rocket design. Konstantin Tsiolkovsky, a Russian schoolteacher, developed the rocket equation. So, a fundamental formula describing how velocity changes with fuel consumption in space. Though he never built rockets, his theoretical work in the late 19th century and early 20th profoundly influenced future designs. Hermann Oberth, a German physicist and contemporary of Tsiolkovsky, Oberth advanced the theory of liquid-fueled rockets and directly inspired many engineers who would go on to build early rockets, including Wernher von Braun. So let's look at World War II and the V-2 rocket. The first practical space-capable rocket emerged during World War II with the development of the V-2 rocket. This was in Nazi Germany. The rocket was designed by Wernher von Braun. The V-2 was the first rocket to reach the edge of space, achieving an altitude of 189 kilometers, that's 118 miles, and this was back in 1944. The rocket was powered by ethanol and liquid oxygen. It laid the technical foundation for all modern rockets. After the war, von Braun and many of his team were brought to the United States under Operation Paperclip, where they would play a pivotal role in America's space program. Meanwhile, the Soviet Union also acquired V-2 rocket technology and engineers, setting the stage for the space race. So let's talk about the space race. The rivalry fuels innovation problem. So, I guess not really a problem, but the Cold War rivalry between the United States and the Soviet Union led to a rapid acceleration in rocket technology. Sputnik and the R-7 rocket. So in 1957, the Soviet Union launched Sputnik 1, the first artificial satellite into orbit using the R-7 Semyorka rocket. So originally designed as an intercontinental ballistic missile, ICBM, the R-7 was adapted for space missions. This event marked the beginning of a space race and spurred the United States to accelerate its own space efforts. Just think about it. You're sitting there and realize there's this unmanned craft, some satellite, some unknown object from an enemy flying overhead that can be heard from all of those down below. This was definitely something the US did not want, so they had to step up their game and accelerate through the space race to overcome the Russians. This brings us to the Saturn V. It was designed under the leadership of Wernher von Braun at NASA. The Saturn V remains the most powerful rocket ever built. It carried the Apollo astronauts to the moon with its first crewed mission, Apollo 8, orbiting the moon in 1968. The iconic Apollo 11 mission in 1969 marked humanity's first ever footsteps on another celestial body. The Saturn V stood 363 feet tall, weighed over 6.5 million pounds, and generated 7.6 million pounds of thrust. This brings us to the shuttle era. Reusability takes the center stage, so 1980s brought a new vision for space travel, reusability. Also a focus of today, but we will get there. So, NASA's Space Shuttle program launched in 1981. The Space Shuttle was the world's first reusable spacecraft. It combined a spaceplane for orbit and return with solid rocket boosters and external fuel tank. Over 30 years, the Space Shuttle carried out 135 missions, including deploying satellites, repairing the Hubble Space Telescope, and constructing the International Space Station, the ISS. Despite its success, the shuttle faced criticism for high costs and safety concerns, highlighted by Challenger and the Columbia disasters. The modern era, commercial spaceflight and reusability. Here we go. The 21st century brought private companies into the fold, transforming the industry and lowering costs. SpaceX. This was founded by Elon Musk in 2002. SpaceX revolutionized space travel with its focus on reusability and cost reduction. The Falcon 9, first launched in 2010, became the first orbital rocket to successfully land and be reused. I emphasize orbital because Blue Origin actually was the first suborbital rocket to successfully land and be reused prior to the Falcon 9 demonstration. So, the Falcon Heavy, introduced in 2018, became the most powerful rocket operational today, capable of lifting 64 tons to LEO. Blue Origin. Founded by Jeff Bezos, Blue Origin developed rockets like New Shepard for suborbital tourism and the new and upcoming New Glenn for orbital missions. Rocket Lab. Aiming for smaller payloads, Rocket Lab introduced the Electron rocket, focusing on rapid, cost-effective launches for small satellites. NASA's Space Launch System, SLS. Designed for deep space missions, the SLS will play a crucial role in the upcoming Artemis program, aiming to return astronauts to the moon and establish a presence there. Well, I'm going to take a step back. I just realized when I mentioned the Falcon 9, yes, it was first launched in 2010 and did become the first orbital rocket to successfully land and be reused, but that was not in 2010. That was not until 2015, I believe. So I just wanted to clarify there so I don't get any comments here saying that it wasn't 2010 that the first orbital rocket successfully demonstrated landing and being reused. That was in 2015, I believe, end of November, early December timeline. All right, moving on. So the breakthrough technologies and future visions. So Blue Origin's New Glenn. This takes a giant leap towards orbital spacecraft. So let's take a closer look then. New Glenn is one of the most anticipated heavy lift rockets in development today. The rocket is named after astronaut John Glenn, the first American to orbit the Earth. New Glenn is Blue Origin's ambitious entry into the realm of orbital class launch systems. Some of the key features and capabilities. So, the size and design. New Glenn is a two-stage rocket standing at a towering 98 meters, or 323 feet tall, very close to the Saturn V. This makes it one of the tallest rockets ever built. Its reusable first stage is designed to land on an ocean platform much like SpaceX's Falcon 9. Its payload capacity, though, boasts a payload capacity of 45 metric tons to low Earth orbit, LEO, which positions it as a direct competitor to rockets like SpaceX Falcon Heavy. So, what powers New Glenn? Well, that's the BE-4 engine. The rocket is powered by 7 BE-4 engines on the first stage, each burning liquefied natural gas, LNG, and liquid oxygen, LOX. These engines collectively generate 3.85 million pounds of thrust, providing New Glenn with the power to carry heavy payloads into orbit. So why did Blue Origin choose LNG, or liquid natural gas? Well, liquid natural gas is less expensive, it's widely available, and cleaner burning than traditional rocket fuels, contributing to Blue Origin's sustainability goals. So when we look at reusability and cost efficiency, well, the first stage of New Glenn is designed to be reusable for up to 25 missions, significantly reducing the cost of launches. Blue Origin's plans to recover the booster via a controlled landing on its massive ocean-going platform, the Jacqueline, which is named after Jeff Bezos' mother. So what about the applications and market impact? Well, New Glenn is designed to serve a variety of missions. This includes satellite deployment for commercial and government customers, deep space missions. Well, New Glenn's capability to carry larger payloads makes it suitable for missions to the moon and beyond. Space tourism and habitats. Well, Blue Origin envisions using New Glenn to support future space stations like Orbital Reef. What about some future prospects then? Although the first flight of New Glenn has faced a couple delays, hopefully by the time this is released, we can say that those delays have been remediated and New Glenn has launched. But we will see what happens. So it remains a cornerstone of Blue Origin's vision for the future of space exploration. With its massive payload capacity, reusable design, and focus on sustainability, New Glenn could become a key player in the commercial space race, helping to democratize access to orbit and beyond. Yes, I definitely believe so, and fingers crossed for the launch this evening, which will be the night prior or early this morning, depending on which time zone you are in. So hopefully, as you're listening to this, we'll have some good news on tomorrow. So we shall see. So New Glenn exemplifies Blue Origin's motto, Gradatum Ferociter, step by step ferociously, marking another exciting chapter in humanity's journey to the stars. So today, the industry is pushing boundaries with technologies such as 3D printing. So I do a lot of 3D printing myself, mostly with an FDM printer. I use mostly ABS and some carbon filaments. I also have a couple resin printers. Super awesome. I enjoy it. But I've never done any metal 3D printing, which brings us to 3D printing rockets. So 3D printing rockets. Rockets like Relativity Space, Terran R, are being 3D printed to reduce manufacturing time and costs. How I wish I had a printer capable of doing that, because I could only imagine the type of designs I could come up with. I actually 3D printed a rocket engine out of ABS a while back, and somewhere on YouTube that video lives where I ignited it and got to see a very quick plume come out the nozzle. This was part of some work I did in my master's program at Florida Institute of Technology during my propulsion course, and had a lot of fun with that. But you can still 3D print some stuff at home with plastics and different polymers. They just won't burn for long. So a lot of fun to experiment, though. Just wanted to throw that in there. All right, nuclear propulsion. So we talked a little bit about this in our basics of rocket propulsion, but we're just going to touch on it here. So again, it offers a higher efficiency and speed for deep space missions. Now, Starship, which is built by SpaceX. It's a fully reusable, and it is designed for interplanetary travel. Starship aims to make Mars colonization a reality. From Goddard's backyard experiments to interplanetary missions, space launch systems have transformed the way humanity views and explores the cosmos. The history of rockets is not just a story of machines, but of the people and their relentless drive to go farther, faster, and higher than ever before. Alright, so what kind of space launch systems exist today? We've talked about the rockets here, but what about the actual types? So, space launch systems come in various designs, each tailored to specific missions. That is why New Glenn might be for one purpose, and Starship is for another, like interplanetary missions. So let's dive a little bit deeper then. So, Expendable Launch Vehicles, ELVs. So an example of this is the Ariane 5 from Europe. It is used once and then discarded. Great for heavy payloads, but not cost effective. Now, reusable launch vehicles, RLVs. A good example here is the Falcon 9, very proven platform. This is by SpaceX. Parts like boosters are recovered and reused, dramatically lowering costs. Air-launched rockets. An example here is the Pegasus rocket. It is deployed mid-air from a carrier plane, allowing flexible launch locations. Small satellite launchers. This is like Rocket Lab's Electron. It is specialized for lighter payloads with shorter turnaround times. Super heavy lift vehicles, the fun stuff. So this is the Starship or SLS, so that's SpaceX and NASA's rockets that they have been building and have launched. Alright, designed for interplanetary missions and massive payloads. Each design reflects trade-offs between costs, payload capacity, and mission requirements. We won't go too much into that just yet, but I will talk a bit about the costs and cost per kilogram to orbit and such as well a bit later in this episode. Alright, so what about the engines that power these rockets? So, the engine is the heart of a launch vehicle. It converts chemical energy into raw thrust needed to escape Earth's gravity. So let's dive a little bit deeper into some of the most important propulsion systems that have driven humanity's journey to space and the innovative engines shaping our future. Let's start with liquid rocket engines. Liquid rocket engines combine a liquid oxidizer, like liquid oxygen, LOX, with a liquid fuel like hydrogen or kerosene for high efficiency and precise control. A good example of this is the RS-25, the Space Shuttle main engine, now used on the SLS. So this was first flown in 1981. The RS-25 is one of the most efficient rocket engines ever developed, with a vacuum-specific impulse of 452 seconds. We previously talked a bit about specific impulse, but we'll mention that it's more or less a measure of performance of that rocket engine. So 452 seconds is quite impressive. It uses liquid hydrogen, LH2, and liquid oxygen, LOX, providing 512,000 pounds of thrust. Legacy. Designed for reuse, the RS-25 engines flew multiple space shuttle missions and are now powering NASA's Space Launch System for the Artemis lunar missions. Alright, let's take a look then at solid rocket boosters, SRBs. These are the motors, as we previously mentioned as well. Liquid, we talk engines. Solid, we talk motors. So here they're referred to as boosters, but same thing. Unlike liquid engines, SRBs use pre-mixed solid propellant that ignites to produce thrust. While simpler and more robust, they lack the ability to throttle or shut down once ignited. A good example of this is the Space Shuttle solid rocket boosters, again SRBs. Each SRB provided 3.3 million pounds of thrust, making them the most powerful solid rocket booster ever built. They burned a mixture of powdered aluminum, that was the fuel, and ammonium perchlorate, the oxidizer, and a polymer binder, that's kind of what keeps everything together. I've seen in some other kind of hobbyist rocket motors and that they use PVC pipes and different types of rubbers as well to help burn as a fuel, which is pretty cool. Definitely encourage you to look that up. If you're into any hobbyist types of rockets, then you probably already know this, and maybe you've even used some of these, so I'd love to hear some of your feedback on that as well. Alright, so contribution. SRBs were critical to the shuttle program, carrying most of the vehicle's weight during the initial phase of ascent. Let's look at hybrid rocket engines. So this is when you have a combination of solid fuel and liquid propulsion. So hybrid engines bridge that gap between the two. They use a solid fuel combined with a liquid oxidizer, offering some throttling capability and increased safety over the fully liquid systems. Starship 2's Rocket Motor 2. Fuel, a rubber-like compound, HTPB. That's Hotel Tango Papa Bravo. The oxidizer used was nitrous oxide, also known as laughing gas. Yes, the stuff they give you during procedures like your wisdom teeth being removed. These engines are relatively simple to design and safer than traditional liquid systems, since the fuel and oxidizer are stored separately. They are commonly used in suborbital tourism and experimental rockets. Methane engines, here we go. Methane-fueled engines represent the cutting edge of rocket technology, with a focus on sustainability and future exploration. Methane is abundant on Mars, which makes it ideal for in-situ resource utilization, ISRU, during Mars missions or other missions to other planets where you can break down those materials. Methane is very cool looking at what it's capable of doing, and for a rocket fuel and future development of, say, Mars, permanent presence on Mars and colonizing Mars. So I know Elon and SpaceX have done a lot of research in this area, and excited to see where that goes. So a good example actually of this is the Raptor engine, which is used on SpaceX's Starship, since we're looking at interplanetary use cases for the Starship and going to Mars. The fuel being used is, of course, liquid methane, CH4. And the oxidizer is liquid oxygen, LOX. It produced a thrust of 500,000 pounds per engine, and delivers a high specific impulse while being reusable for multiple flights. The Raptor engine is a full-flow staged combustion engine, meaning that all propellant is burned, maximizing efficiency and minimizing waste. Its role is to power both the first and second stage of Starship, SpaceX's fully reusable Mars vehicle. Let's talk a little bit now about the BE-4, Blue Origins. So we previously mentioned it earlier in this episode, but we'll go a little bit more into detail on the engine itself. So the BE-4 is Blue Origin's state-of-the-art engine designed for New Glenn and ULA's Falcon Centaur rocket. It is fueled by liquefied natural gas, LNG, and again, the oxidizer is liquid oxygen, LOX. It produces 550,000 pounds of thrust per engine. We already mentioned why LNG, being that it is cost-effective and widely available alternative to other rocket fuels. It's also cleaner burning and reduces engine maintenance, which enables more reusability. It is also a full-flow staged combustion. Like the Raptor, the BE-4 uses this advanced design to increase efficiency and thrust. Now, what are some of the goals here? Well, it's designed to be reused up to 25 times, which will help contribute to those lower launch costs and lower cost to orbit. Each engine type plays a unique role in the broader landscape of space exploration, from launching cargo to the International Space Station to propelling humanity towards Mars and beyond. By leveraging these propulsion technologies, we continue to break barriers and redefine what's possible in space travel. Alright, now the costs of launch and what everybody hates, scrubbing. Alright, so rockets aren't cheap, that is for sure. Launching a payload into orbit is one of the most complex and resource-intensive undertakings humanity has ever developed. Costs can range from tens of millions to well over $1 billion per launch. This depends on the rocket, mission, and the payload. So let's break this down and compare the costs of some of the key systems like the Falcon 9, SLS, and New Glenn. Starting with Falcon 9, SpaceX. So the base launch cost is around $67 million for a standard Falcon 9 mission. This is among the most cost-effective options currently available, thanks to SpaceX's focus on reusability. Now, what is the impact of this reusability? Well, the ability to recover and reuse the first stage of the rocket has reduced costs by approximately 30%, as components like engines, structures, and other parts of the rocket don't need to be rebuilt from scratch after each launch. So, in comparison to traditional rockets pre-SpaceX, comparable launches often exceeded $200 million, primarily due to the expendable nature of those rocket systems. Now let's look at the Space Launch System, SLS. Heart of the Artemis. So, what are the launch costs here? It is estimated at about $4.1 billion per mission for an Artemis flight. Wow. The SLS is a non-reusable heavy lift rocket, which significantly drives up costs compared to reusable systems. So why is this so expensive? We just mentioned Falcon 9 starts at $67 million. This is $4.1 billion. So why? Alright, well, the SLS uses heritage technology from Space Shuttle and Apollo missions. This involves legacy infrastructure and supply chains. Each RS-25 engine, originally designed for the Space Shuttle, costs around $146 million, and 4 are used every launch. Solid rocket boosters, though powerful, are discarded after use. So just the cost of one engine, $146 million. That's more than twice, or launching 2 times of a Falcon 9. So, something to think about. Alright, so the impact. While it's the most powerful rocket ever built, its high cost limits launch frequency, making it more suitable for flagship missions like crewed lunar landings. New Glenn. So again, Blue Origin. This projected cost is estimated at about $500 million per launch, though the exact figures may vary depending on the mission. Now, we don't have the breakdown here, and I probably should have done it for Falcon Heavy, which is 3 boosters, kind of a Falcon 9, not exactly, but you can take that amount, maybe multiply it by 3 and add some buffer, remove some buffer, but still, Falcon 9 definitely and Falcon Heavy are more or less the cheaper options of all 3. So what about reusability then? So like Falcon 9, New Glenn is designed with reusable first stage, which Blue Origin claims can fly up to 25 times before requiring any type of major refurbishment. Capacity. So it offers a significantly higher payload capacity compared to that of the Falcon 9. This makes it a competitive option for large commercial and government missions. The target market, though, so New Glenn aims to serve a broader array of missions, from deploying large satellite constellations to interplanetary exploration, balancing cost effectiveness with capability. So let's take a look at some cost comparisons here more directly. So cost comparison. So we're going to look again between the Falcon 9, the SLS, and New Glenn. So the launch cost we already mentioned, $67 million for Falcon 9, $4.1 billion for the SLS, and roughly $500 million for New Glenn. Reusability, well, both New Glenn and Falcon 9 have a reusable first stage. SLS is non-reusable. What about payload capacity, though? So this is where things start to differ quite significantly. This is a payload capacity to LEO, just for reference. So the Falcon 9, roughly 22,800 kilograms. New Glenn, 45,000 kilograms roughly. But SLS is able to do 95,000 kilograms. That is why it is currently being used for these crewed missions to the moon, because its capability to put such a heavy payload. Now, for missions that don't require such a big payload or such payload capacity, systems like the Falcon 9 or New Glenn could be quite suitable. For example, Falcon 9 launched I think it's called Blue Ghost last night. That is a lander to the moon surface to do some research there. So that's an unmanned mission. But Falcon 9 was quite capable of delivering that payload. All right, cost efficiency. So this is the cost per kilogram to low Earth orbit, LEO. Falcon 9 takes it away here. So $2,900 per kilogram, with New Glenn at $11,100 per kilogram, and SLS with a whopping $43,000 per kilogram. So while Falcon 9 leads in cost efficiency, New Glenn seeks to strike a balance between reusability and high payload capacity. SLS, while the least cost efficient, remains indispensable for deep space missions due to its unparalleled lift capacity. The cost of scrubs. Dun dun dun. Alright, scrubbing a launch. We all hate it. Most of us have experienced it. If you've ever gone to see a launch and been turned away or waited hours and hours, lost sleep, and then realized the launch is not happening, it can be quite disappointing. But what is even more disappointing? The cost. So canceling a launch, whether due to bad weather, technical issues, or a range of violation, this adds significant costs. So let's look at fuel to begin. So fuel costs. Liquid oxygen, liquid hydrogen, and methane are not only expensive, but also time sensitive. Some must be vented or replenished before reuse. Then there's labor. Every scrub requires teams to reset, inspect, and prepare the rocket once again. Different rockets have different crew sizes. Some of them have significantly more. And those are all individuals, engineers, people that you have to pay in order to do these tasks. So there's the logistics. So delays can disrupt schedules for downstream missions, particularly at busy launch sites like Cape Canaveral on the Space Coast of Florida. So here's some example scrubbing costs. So the Falcon 9, we'll start again here. So scrubbing a launch might cost an additional $500,000 to $1 million, depending on how far along the countdown was. Obviously, closer you get down to the T-0, then the cost goes up. SLS, given its massive scale, a scrub could cost millions of dollars in fuel and labor alone. For Artemis 1, multiple scrubs delayed the mission and added weeks of work, showcasing the financial stakes of getting it right the first time. Now, with any new rocket, I want everyone to understand, getting it right the first time, highly unlikely. If you're a computer scientist and you write code, how many times does a piece of code you write the first time actually work? Same thing goes here, except for at a much more complex and significant scale. So, usually when there's a scrub, it is for a very important reason or safety reason or something along these lines. And with space and the dangers that come along with it, we definitely rather see a scrub than pushing forward with something that might put engineers, astronauts, payloads, or anything else really at risk. So just wanted to point that out, that even though the scrub might happen, there's typically a reason for this, and it's usually the right call. Alright, so why does this even matter? Well, efforts to reduce costs through usability, streamlined operations, and efficient fuels are making space more accessible. While SLS represents a traditional flagship approach, rockets like Falcon 9 and New Glenn are showing the way toward a sustainable, cost-effective future in space exploration. Each scrub or delay reminds us of the precision and dedication required to launch humanity beyond Earth. So we're almost ready to wrap things up here, but I just want to quickly talk through a few other things about orbits, launch sites, and that before we kind of close things up here. So what about these orbits and launch sites? So rockets deliver payloads to different orbits depending on the mission. Their ability to launch to different orbits also depends on their location. So let's look at low Earth orbit LEO. So this is great for satellites like Starlink. Geostationary orbits, GEO, ideal for communication satellites, or say GPS. Translunar injection, so this is for missions to the moon and beyond. Launch sites are chosen based on their proximity to the equator for a rotational boost. So think of it as you spin a ball, the center of the ball versus the poles of the ball. So the part that is widest is at the center and has a faster velocity in the direction of rotation. This helps you give a little bit of a boost. Think of it like running and throwing a ball versus standing still and throwing the ball. When you're running and throwing the ball, it'll go a bit faster. So that's the boost we get from launching a bit closer to the equator where able. So major launch sites here include Cape Canaveral in the US, Baikonur Cosmodrome, that's in Russia, Kourou Spaceport in Europe, Wenchang in China. All right, those are some of the launch sites we'll mention, but what about the future of these launch systems? So the exciting developments are on the horizon. Starship by SpaceX, and I'm sure during this episode being recorded right now, we are supposed to have Starship 7, so very exciting. Hopefully that also goes tonight and the weather clears up for them. That is a fully reusable rocket launch system which is designed for Mars. Blue Origin's New Glenn, aimed at heavy lift missions. Also hoping this happens tonight, over the night, depending on time zone again. But lots of stuff going on today while recording this episode. All right, Rocket Lab's Neutron, combining reusability and precision. And emerging technologies like 3D printed engines and nuclear thermal propulsion could further revolutionize the industry. So, space launch systems represent humanity's ingenuity and determination to explore beyond Earth. From the Saturn V to the Starship, each rocket tells a story of innovation and adventure. And that is all I have for you folks today. So thank you so much for joining me on the RedMars Podcast. Apologize for this one going a bit longer, but there's just so much information to get through. And even what I talked through today is very much just the tip of what could be discussed for these launch systems. We can go much more into detail on each individual one of these for probably much over an hour on each one, but we'll save that for another time. So for now, thank you all. Have a great rest of your day. Hopefully we'll be talking about the success of Starship number 7 and New Glenn in our next episode. And until then, stay curious and keep looking up.